Welcome Earth and Space Science students to the Dallas Independent School District STEM Environmental Education Center. We know you can't be here in person, but we're going to do our best today to make you feel like you're out here at the center learning about star formations. If you are watching this and have not registered for this morning's field trip yet, you can still do that by going to www.tiny.cc/EEC register to get yourself or your class registered for this field trip. We just use that information for our attendance purposes. And like I mentioned a minute ago, today's field trip is going to explore star formation. So during this virtual field trip, students will investigate how the sun and other stars transform matter into energy through nuclear fusion. So we are going to explore the origin and history of the sun, look at the sun's structure, scale, and composition, explore nuclear fusion, and the formation of stars. And while we do all of that, you can ask us questions, but since this is a virtual field trip, you'll need to do that through this website, which is www.tiny.cc/EEC-question-answer. And you can ask us any questions related to star formation that you like, and as many questions as you like, and we will do our best to get them all answered in the time that we have with you this morning. So without further ado, I'm going to stop sharing my screen here and turn it over to Mr. Monroe, who will get us started with the origin of the sun.
Okay, good morning, students. My name is Mr. Monroe, and I'm going to be giving you some information about the origin of the sun and a little history of the sun. You know, the sun is a part of our solar system, and our solar system is part of the galaxy. And there's not just one galaxy that exists in the universe, there's a whole bunch. But you know, the early belief about the sun was the fact that some of the cultural groups kind of referred to the sun as being a god. And then we have other cultural groups that deem the importance of the sun. In fact, the American Indians that belong to the horse culture that use the teepee as a dwelling place, they believe that the sun was the source of all life. And in fact, when they put their teepees up, they always make sure that the door faced the east, because the sun rises in the east as far as the inhabitants on the earth here. And they felt like, what better way to wake up in the morning than to see the source of all life? And of course, you know, questions are asked, where did the sun come from? Did it have a beginning? Will it ever end? And you know, there is a theory, and this theory is called the Big Bang Theory. And it states that 13.7 billion years ago, the universe was born, along with our sun, okay? And according to this theory, it started from a little tiny spot, no bigger than an atom. In fact, some say it was no bigger than an electron. This little tiny spot was referred to as a singularity. At that time, all matter, energy, and space was condensed into this little spot. Then all of a sudden, something happened. A tremendous expansion began. And it didn't take long for it to begin. It just happened. Very similar to an explosion, although it wasn't an explosion, from what I understand. Now, there are several sources of evidence that support the Big Bang Theory. And I'm briefly going to talk about some of that evidence with you. The first source of evidence that I want to discuss with you is light abundance, or light element abundance. The Big Bang Theory predicts that certain percentages of light elements were in the universe. These predictions also were supported by data. The abundance of light elements in the early universe can be compared with abundance of light elements in the stars today. To do this, scientists study stars that are very far from Earth and early stages of development, okay? Scientists analyze the spectral lines of these stars to determine the amounts of the elements being produced within their cores. The percentage of light elements in these stars are very close to the theoretical values predicted by the Big Bang Theory. Now, the other source or evidence source is that there was a redshift of galaxies. The expansion of the universe also supports the Big Bang Theory. An astronomer by the name of Edwin Hubble found redshifts in a spectra of galaxies that he was studying that he had actually observed. The redshift showed that the galaxies are moving away from the Earth in all directions. Also, galaxies are moving at speeds proportional to the distances from the Earth, their distances from the Earth. The further a galaxy is, the faster it is moving. Okay? Hubble concluded that the distances between the galaxies and galaxy clusters have been increasing over time. Because galaxies are moving apart, guess what? He figured out they must have been closer together in the past. This is consistent with the idea that the universe has been expanding since the Big Bang happened. The other source of evidence deals with cosmic microwave background. The early universe was made up of very hot particles. These particles absorb and emitted visible and ultraviolet radiation. The universe cooled rapidly in its expansion. The radiation also spread out and it cooled. Its wavelengths stretched into the microwave range. The universe today should be filled with traces of this early radiation called cosmic microwave background. In other words, CMB. CMB can be detected by infrared and radio telescopes. In 1965, radio engineers Arno Penzias and Robert Wilson were using an antenna that transmitted telephone calls to orbiting satellites. They noticed a faint background signal from every direction in the sky. They discovered that they were picking up CMB, cosmic microwave background. The temperature of this radiation was very cold. This temperature is similar to what scientists predicted the temperature would be after the universe cooled for billions of years. I don't know whether you can see it, but this diagram shows kind of like a Big Bang Theory timeline. At 400,000 years after the Big Bang, that's when the cosmic microwave background began to appear. During this time, the inflation was going on. At 400 million years ago, at 400 million years from the Big Bang, it says that the first stars started appearing. If we get to the point to when our solar system was developed, that formation happened about 8,700,000,000 years ago. And it brings us to the point now of 13.7 billion years ago. That's when the Big Bang happened. Now, that's the most acceptable theory that scientists have come up with in the creation of our solar system, our galaxy, and the many galaxies that are in the universe now. And it seems like there's a lot of evidence suggesting that evidence suggesting that the universe is still growing and expanding. Now, I'm going to turn it back over to Mr. Broughton. And if any of you have any questions, he'll answer those for you if he can. Mr. Broughton?
Yep. Thank you, Mr. Monroe. So you did talk about the Big Bang Theory, and a student asked, what is the difference between a hypothesis and a theory? A hypothesis is a more tentative statement. It does need to be a testable statement, and then it's either supported or not supported by evidence. And a theory can become a theory if that hypothesis has been tested over and over again over usually years under a wide variety of conditions by different scientists all over the world. And if they all can support that theory, the hypothesis, then that hypothesis can become a theory. All right, now we're going to look at the structure of the sun with Ms. Ramirez.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about the structure of the sun. Just to review, the sun is just a yellow dwarf star, and it is at the center of our solar system. The sun is so massive that its gravity holds together pretty much our solar system and all the planets within it. So the sun is just a star, and to show you size comparisons between how massive the sun is, let's look at this example. If the Earth were the size of the pinhead on this pin, then the sun would be the size of a basketball. So this is a good example of the relative sizes of the sun and the Earth. Another good way to demonstrate the size is with this little infographic here. You could fit 1.3 million Earths inside the sun. And if you were to talk about the diameter of the sun, you could fit 109 Earths lined up to go around the sun. So that's just how massive the sun is. The mass of the sun takes up about 99.86% of the mass of our entire solar system. And that's the sun. So now we're going to go ahead and take a look at some of the parts and structure of our sun. And before we do that, I just have a little quick video from NASA to show you guys. This would be a good time to take out a science notebook if you have one, open up to a fresh page and grab a pen or pencil, something to write with, so that you can make some observations about what you're seeing in the video. So we're going to be looking at some images of the sun, document, draw, label what you're seeing in the video, and also make some questions or wonderings about what you have. So I'm going to go ahead and share my screen, and we'll show you the video. So we're not going to watch the entire video. We're kind of going to go look at little pieces of it. You're thinking about, what do you think you're seeing? Can you identify any structures? Think about any questions you might have. And we're going to stop it there. So our sun is just a giant ball of hot gases, mostly hydrogen and helium. And one of the questions I had when I was watching this video was, how come the sun is represented with different colors? And the reason for that is scientists actually use different wavelengths to observe the sun with the telescope. So depending upon what wavelength they're using, they can actually identify different parts or different structures of the sun. So this diagram just shows an example of some of the wavelengths that they're using and how the sun is represented with those wavelengths. Another cool thing is, you should never look at the sun with your naked eye. It would damage your eyes. But something cool is there is the largest solar telescope in the world is actually in Hawaii. And they just released their first images back in January. And this has some cool images. This is from the National Solar Observatory. And it has some cool images of the internal parts of the telescope, and then you can just see how massive this telescope is, because here's the outside housing for the telescope. So it's really cool to see this. They can get some really nice images. So if you're interested in learning more about solar images using telescopes, this is a great website for you guys to visit. So I'm going to stop sharing our screen, and we're going to continue on with our presentation. We're going to go ahead and dive in deeper about the parts of our sun. So I'm going to give you guys a description, and we're going to see if you can identify what structure or layer we're talking about. So the first part that we're going to talk about is known as the center of the sun. So that should be a good giveaway. And what do you think we call the center of the sun? That would be this area right here, and that is the core. So the core is over 27 million degrees Fahrenheit. It is so hot in the core of the sun that nuclear fusion takes place there, and that is what releases the energy that powers the sun. It provides us with light and also heat energy as well. All the energy that's being radiated out of the core will make its way outward into the radiative zone and into the convective zones. Our next layer that we're going to talk about is also known as the surface of the sun. So what area do you think represents the surface of the sun? That would be the photosphere. So the photosphere is simply the sun's surface, and it's the area of the sun that we typically see. It is over 300 miles thick, and it's not a solid layer like our Earth. So planet Earth is a rocky planet. We have a solid rocky surface that we can stand on. The surface of the sun, the photosphere, is made out of entirely gases. So remember, the sun is just a star. Most of the light that comes out from the photosphere, that is what we're going to be seeing. And it takes about 8 minutes for us to see that visible light from the sun. So that shows how the distance, how far away our sun is. Now on our photosphere, you also see these spots. Those spots are called sunspots. The scientific word for sunspots are macula. Macula are just large vortexes that form on the photosphere, and they are formed because of the sun's differential rotation. All that means is different parts of the sun rotate at different times. So unlike planet Earth, so planet Earth rotates once every 24 hours, and it's consistent throughout the entire planet. Because the sun is so massive, the equator, it takes about 25 days for the equator to rotate once, but on the poles, it can take up to 35 days. So because of that differential rotation, it creates vortexes in the photosphere, and that is what's creating these swirly sunspots. Sunspots are not permanent. They will come and go. And when we have sunspot maximums, which on our 12-year cycle, those sunspot maximums usually give us high electromagnetic fields, and we usually see a lot of solar flares during our sunspot maximums. The next layer we're going to talk about is the part of the atmosphere that we don't typically see on the sun because the photosphere is so bright that it blocks out the light from this layer. This next layer is called the chromosphere. So the chromosphere, again, the light from this layer is too thick for us to see. The only time we can see the chromosphere is during a total solar eclipse. So let me show you a demonstration of what I mean by a solar eclipse. This model represents a solar eclipse. All that's occurring during a total solar eclipse is a new moon is passing in between the Earth and the sun. And from our vantage point, the moon is blocking out a large portion of the sun. It's blocking out that photosphere. So all we see left is the chromosphere. And when we look at the sun during a total solar eclipse, we see a red light or a red rim. That red rim is the chromosphere. And I have on our little sun, we have some solar glasses. We actually used these solar glasses back in 2017 when we had a total solar eclipse. So again, you never want to look at the sun with your eyes. It could seriously damage you. So this is our total solar eclipse. And again, the only time you're going to be able to see that nice red chromosphere is during a total solar eclipse. And from our chromosphere, we actually have these cool looking fiery projections, and that are this area here. These are prominences. So a prominence, they are just like flames of hot gas that erupt out of the chromosphere. They can eject over 100,000 kilometers into the sun's atmosphere. They can last for minutes, hours, days, or even months. The next layer that we're going to talk about is often called the crown of the sun. So do y'all think y'all can identify that in this diagram? The crown of the sun is the easy one to me. It's called the corona, and it's all of this white light out here. So the corona is a very thin gas layer, and it's the outermost layer of the sun's atmosphere. The corona is actually much hotter than the surface of the sun, or the photosphere. Now, a lot of people tend to think that the further away you get from the core, the cooler it's going to get. But instead, for the sun, it's actually hotter. So the corona is much hotter than the actual photosphere of the sun. It's up to 2 million degrees Celsius. And again, it's usually invisible except during a total solar eclipse. And that's, again, just because the light from the photosphere is so much brighter. So just to review some of the things that we saw, we're going to look at this little 3D model. So remember, we have our core, which is the center of the sun, and that is where nuclear fusion takes place. We also have that radiation from the core going out into the radiative layer and into the convective layer. And then we have what's called the surface of the sun, and that was our photosphere. The photosphere is the surface of the sun, and that is where we start to see the macula or the sunspots. And again, those sunspots typically follow a 12-year solar cycle where they go through minimum and maximums. Then we have our chromosphere, which is the atmosphere layer of the sun. It is much hotter than the photosphere. And from the chromosphere, we start to see these projections called prominences. And these prominences are just flames of hot gases that are erupting from the chromosphere. And again, typically, we're not going to be able to see that beautiful chromosphere because the photosphere is so bright. And then we have, lastly, our crown for the sun, the corona. And again, unfortunately, we're not going to be able to see that corona until we have a total solar eclipse. So those are the main parts and structure of the sun. I also have an app that I want to show you guys. I know it's kind of hard to visualize the sun since we can't actually see it with our own eyes, and we need special telescopes for it. But this app is called Solar Walk Lite, and it's a free app that you can put on your phones or tablets. And it gives you like a 3D simulation of not only the sun, but the other planets. In this case, we're not going to look at the other planets. Oops, we're going to look at the sun. And you can zoom in on the sun. And today we're going to focus on the sun. And if I hit this little info button, you can make the sun rotate. So the sun rotates just like planet Earth does. And it also shows you an image of the internal structure. So you can read about the internal structure. You can play around with rotating it and looking at it. It also gives you information for you to read, facts, beautiful pictures and images in a gallery. So this is just a fun app for you guys to play around with to learn about the sun structure as well as the other planets. And the last thing I have for you guys is just a challenge question to put all the stuff together that you learned. My challenge question for you guys is to see if you can compare and contrast the structure and composition of the sun with that of our own planet Earth. So y'all should already be familiar with planet Earth. So see if you can compare and contrast similarities and differences between the sun structure and our very own planet. The last thing I have for you is just a reflection question. And I want you guys to think about, how does the sun affect you and others? And then what are some of the benefits that our sun provides? And are there any dangers that the sun might relate to us? And that's all I have for you guys today on the sun structure and composition. We're going to give it back to Mr. Broughton if you have any questions. Thank you.
Thank you, Mr. Ramirez. I downloaded that app, and it is pretty cool. The question that we got was, do you have a solar telescope at the center? And yes, we do. And actually, I have it right here with me. It's not very large. It is a Coronado PST, which stands for Personal Solar Telescope. But even though it's small, it does work. It allows us to see things like sunspots and solar prominences on the sun. So it's a pretty useful tool. And the way it works is that if I kind of aim this in there, you can see how the lens is bluish. Kind of reminds you maybe of sunglasses. That is because this filters out the light. It looks like a regular telescope, but it is a solar telescope, so it has to filter out that sun's light so you don't hurt your eye. This ring can kind of fine-tune the contrast between light and dark on the sun, especially for those sunspots. This little knob focuses. Here's the eyepiece that you would look into, and if I take that off, you can see inside there. It's kind of bluish even in there because, again, this is designed to protect your eyes from the sun. You should never use a regular telescope to look at the sun or you would go blind. Now we're going to move into nuclear fusion with Mrs. Fuller.
Good morning, boys and girls. We're going to be talking about nuclear fusion. This is an aspect of heliophysics. Heliophysics is the study of the sun and its relationship with the Earth and the solar system, including the solar weather. Now, nuclear fusion takes place in the core of the sun. Ms. Ramirez just explained to you all the layers of the sun. So just like our planet has a core, the sun has a core, and that's where nuclear fusion takes place. About half of the mass of the sun itself is in the core, but the core only takes up 1/64th of the volume of the sun. So you've got a very small space with a tremendous amount of material. Most of the material is is hydrogen, and the sun converts that hydrogen into helium during the fusion process. Now, the core of the sun is extraordinarily hot, about 27 million degrees Fahrenheit, and the pressure in the core of the sun is about 3 billion times what the air pressure is here on our planet Earth. So you can see a tremendous amount of pressure and a tremendous amount of heat are what make nuclear fusion possible. Now, it's from this nuclear fusion that we get light energy and heat energy emanating from the sun, and that's how it involves its relationship with the Earth and the other planets. Most of the energy that we use here on planet Earth comes from the sun. And the most important chemical reaction that we have here on Earth, photosynthesis, has to happen with light from the sun. Photo means light, synthesis means to make something. So green plants make food, sugar, with light from the sun. So let's talk for just a couple of minutes about how the nuclear fusion happens. It takes four atoms of hydrogen to form one atom of helium. Well, how does that happen? Well, a lot of people think it takes two because hydrogen has one proton and helium has two. So they think it's two atoms of hydrogen, but it's actually four because the two atoms that form the helium are actually isotopes. Now, you know about isotopes. And the first isotope is called deuterium. It's very interesting. It's got twice the mass of regular hydrogen because it has both a proton and a neutron. Regular hydrogen just has a proton. So deuterium, we know it here on Earth as D. It's written as D. Sometimes it's written as 2H because it's twice as heavy as a regular hydrogen. And you may be familiar with a term called heavy water. During the Second World War, heavy water was developed using deuterium, and it was used in the manufacture of bombs, atomic bombs. And there's a real interesting story about Norway's deuterium plant, its heavy water plant using the deuterium, and how the Nazis stole it from them. So I'm going to show you how it's written. Instead of water, H2O, heavy water is written as D2O. So it's two atoms of deuterium and one of oxygen, heavy water. And sometimes deuterium is written as 2H. All right, so we've got this isotope, and it's very stable. It's a very stable isotope. Then you've got an isotope down here called tritium. And tritium is a very rare, but it's radioactive isotope of hydrogen, but it's found naturally here on Earth. It's caused by cosmic rays interacting with the upper atmosphere, and you may even have some in your body, and it's not illegal to own it, but tritium is the form of hydrogen that puts the H in H bomb. So it's used in nuclear weapons. And it's got 1 proton and 2 neutrons. Well, in the tremendous heat and pressure of the core of the sun, these 2 isotopes come together in a very forceful way, and it produces 1 atom of helium. It releases 1 neutron, and it creates heat and light energy. And that heat and light is what we receive from the sun and helps life to exist. So fusion's very interesting, but we don't have the means here on our Earth to economically and safely control nuclear fusion because it's so much cleaner than nuclear fission, which is a splitting of atoms. This is a coming together to create helium. And but the name of the game in energy production is finances, and we can't do that now. There was an idea some years ago about something called cold fusion, and we really cannot do that. There were some scientists who tried it, but they said too much heat was generated from it, or the theory was that it would generate too much heat. So let's see, we got anything else I want to bring up to you? I think that's about right. If you have any other questions about fusion, I'm going to turn it over to Mr. Broughton, and he's going to answer any questions you might have. Have a delightful day. Bye-bye.
Thank you, Mrs. Fuller. And the question that a student submitted was, what is the difference between nuclear fusion and nuclear fission? Nuclear fusion, like Mrs. Fuller said, is when 2 low mass isotopes can fuse together to form like 2 hydrogens. Well, 4 hydrogens will form a helium. That is fusion when they come together. Fission is when you split a large isotope apart. So like a common isotope that's used in nuclear power reactors is uranium-235. They will split that, and that produces a large amount of energy. Although another difference between nuclear fusion and nuclear fission is nuclear fusion produces even more energy than nuclear fission. All right, now we're going to explore star formation with Miss Nash.
Hello, students. Just to remind you that we do actually have a source of nuclear fusion that we could use for our own energy needs, and that would be our very own sun. So lots of ways to use that energy cleanly, safely. Okay, so we're talking about where stars form. And it turns out, oddly enough, that the universe is a very dusty place. Who knew? And there's something out there, big clouds of dust. We call them nebula. Gases, hydrogen gas and dust, we call them nebula. And they're kind of spinning around out there in space. And of course, gravity works in outer space also. And they gradually begin to clump together. So we call this the star-forming nebula, a cloud of mostly hydrogen. And a star-forming nebula, that's our first stage. And then, if you were having an invention, and you invented something really smart, maybe to use solar energy, and you made a model of your invention, you might call that a prototype. So as our star begins to form, we call that a protostar, the beginnings of star. Gravity is clumping the dust and gas together. As it gets clumped and clumped and clumped, it gets hotter, hotter and hotter. If it gets hot enough, fusion can begin. At that point, we have stars. And our star, the sun, is a kind of medium-sized yellow star. Not a particularly big star, but actually that's a good thing for us. Now, there are many different sizes of stars, very hot they are, how big they are. And those big, big, big hot ones, we call them the blue ones. And we think of blue as being a cool color. But in terms of heat, like you have a match, that blue part, or a fire in the fireplace or a campfire, that blue part is the hot part. So those big, big stars and our medium-sized stars and smaller ones, those live for a long time. The stars go through a life cycle, and they will be different sizes and shapes and heat, okay, throughout their life. This is the point of their life where they spend the longest time. And we call those main sequence stars, because that's where most of them are, and for the longest time. Now, I said it was lucky that had a star like this, because this one, these guys last a lot longer than those big giant ones. They burn out faster. Okay, so the main sequence star, there are two forces operating: gravity pushing in and fusion pushing out. And in the main sequence, those two forces are imbalanced. They're imbalanced. But then, after a while, that hydrogen that's being fused in the core, we run out of hydrogen. Uh-oh. So at that point, we get what we call the red giant. And our sun will do this too. And when that happens, well, it'll be over for us. Because what will happen is the core runs out of hydrogen. There's no more fusion pressure out, but the force of gravity is still there, and it comes back in and it collapses and it gets really hot again. It's hot, 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 and now it's hot enough to fuse. Remember what the hydrogen is becoming? Helium. So now it starts fusing helium and expands out again to an enormous size. And we call those the red giant. Now, our sun will do that too, and it will expand outward and engulf most of the solar system. But we'll be gone by then. It'll be a long, long millions, billions of years from now. Now, so don't worry. But the big stars, it's going to happen, that same process will happen over and over, fusing different elements over and over, until finally it gets to iron, and it can't fuse iron. And so at that point, we get our big explosion. Remember I said it was a cycle, because it's going to explode, and everything, all those elements and everything get thrown out into space. And guess where they go? They go out into the nebula to become another nebula. You start the whole thing over again. And that's why we call it a cycle, a life cycle, even though they're not really alive. But they do have a cycle of stages. Now, our sun, after that happens, so everything gets thrown out, and then the core is just there, collapsed, really super, super dense. So two things can happen. If the big star, to the big stars, kind of the regular big star can become the collapsed core becomes a neutron star. In a super, super gigantic one, humongously huge, the collapse, it's so dense that it forms a black hole in which even light cannot escape. So we think there's a black hole at the center of our galaxy. Don't go there. Now, our planet, our sun, when our sun collapses, or suns our size, stars our size of our sun, medium to small, when they go to that last point, after the red giant stage, and they collapse in, they form what we call the Planetary Nebula. It doesn't really have anything to do with planets, but when people first saw these, before they had really great telescopes, and they saw these things through their telescope, and they saw a big cloud, a nebula, because they already named those. In the middle, there was this thing, and they thought, oh, it's a planet. And they called it a planetary nebula. But what that really is that dying star. That dying star. A planetary nebula. Don't be confused by the name. It has nothing really to do with a planet. This is what's going to happen to our sun. Now, I have a couple questions for you here. One is, let's see if you can name those stages. There are 5 stages. Can everybody name the first one? It's a nebulous answer. The nebula, star-forming nebula. That beginning star, a protostar. Then we have our main sequence, and we call them main sequence because that's where most of them are for the longest time. Then we have our red giant, and that stage can happen over and over. And then finally, we have our supernova or our planetary nebula. Now, supernova, we can see them from Earth, and we haven't had one in a long time, so we can cross our fingers and hope to see one soon. I'm hoping. The Chinese have been keeping written records for a long, long time, and they call them visiting stars. They can be seen in the daytime up there with our sun. So pretty amazing. Now, my next question is, why do some stars end in a supernova while others form a planetary nebula? Some become a supernova and others do not. And why? What's the difference between the beginning star and how it ends? And then a final question. How is a stellar life cycle different from a biological life cycle? So I want to thank you for your attention. I hope you enjoyed yourselves, and I want to encourage you to remember that we are all stardust. So all the elements that make up our planet, make up us, all the wonderful things that we enjoy on planet Earth, all of that came from those gigantic explosions, okay, of the supernova. So something to think about. Thank you, and if you have any questions, Mr. Broughton would be glad to answer.
Thank you, Ms. Nash. There was one question, was when will our sun become a red giant star? And scientists estimate that it will take about 5 billion years for that to happen. So we will be long gone by the time that happens. I'm going to share my screen now so we can do a quick recap of what we did today. And so during this virtual field trip, you investigated how the sun and other stars transform matter into energy through nuclear fusion. We explored the origin and history of the sun. We looked at the sun's structure, scale, and composition, discussed nuclear fusion and the formation of stars. So thank you so much for joining us this morning. We appreciate you taking the time to learn about star formation with us. And we do want to know what you thought about today's field trip, and you can let us know by going to www.tiny.cc/EEC feedback to fill out a short form to let us know what you thought about today's field trip. We use that feedback to improve what we do here, and we do value your opinion. So now I'm going to stop sharing my screen and wish you a great rest of the day. Bye-bye.